guys doing okay? Alright, don't look up here if you guys have the conditions you need. Okay, I'm gonna solve, but don't look at it yet. Have some willpower. You have all the conditions you need? Yeah. Hold on. I balanced 2 there. Oh, yeah, 2 here. In the case of using the ratio, yes, you should use. Yeah. All the volume of gases remaining. Okay. Alright, so let's review part of this, because this is a long problem, okay? So you had your issues, you had your conditions given for methane, for oxygen. After you found the conditions, you noticed that it was an ideal gas law problem, so you found the N value. I just shortened my work a little bit, so I was finishing in a same time you guys were. So what I did was, after labeling each of the identities of the conditions and solving for N, I just said PV over RT. So you guys got 0.1888 moles for methane and 1.7529, and I just extended my moles because we don't want to round yet. You guys good there? Shake your heads, okay. So you know that this now is a linear integration problem because you have 2 initial reactants given to you with no condition who's going to be controlling the end product. So this is a BDA table at this point. Can I scroll down some? Yeah. So as you take into consideration the moles of methane and then the moles of oxygen and you divide by your original coefficient, then this one's definitely in excess of the methane's limiting reagent. So as you subtract your limiting reagent, add your limiting reagent, you're still taking into condition the ratios at which they react. So this is a 2 moles of oxygen over 1 moles of methane reacting, and then 1 mole of carbon dioxide being made, and 2 moles of water being made as it relates back to the 1 mole of methane. So after you subtract 0 for your after of your limiting, you should get 0.37 or 1.375 blah 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 moles of oxygen. So this is gas that's remaining. This is gas that was produced, and this is, just because we're dealing with gases right now, this may not be gaseous, but it's really hot. So like we can't always assume that water vapor, that water vaporizes, but this is really hot. What was the temperature condition here? 125 Celsius. When does water boil? 100 degrees Celsius. So now we have some facts to back up why we assume this was gas. So once we had all of our gases and the leftovers remaining from the product or the initial reactant, the first question was to take the carbon dioxide to volume, given these new conditions. P and T of 125 Celsius and 2.5 atmospheres. I definitely converted this to what first? Kelvin, so that was 398 Kelvin, and that plugged it into the ideal gas law, rearranged to solve for volume. So 2.47 liters should be your your carbon dioxide volume. Okay, so remember that you could do ideal gas law for this one, and separately ideal gas law for this one, and then we had this ideal gas law already to solve for volume. So you technically could do the ideal gas law 3 times, solve for 3 volumes, and then add them up, or we were able to do this yesterday. Since we have pressure is caused by collisions only, volume is also going to be impacted by that. We don't care about the identity of the gas, so we can total our moles together, which is what this boom, boom, boom is talking about here. And then once you solve for total moles, multiply by R and T, divide by P, and you should get about 25.4 liters. Yeah. Because the pressure and volume are all related to collisions, like number of collisions with the container wall, and we assume that the particles at the same temperature are moving at the same velocity, so they're hitting the walls with the same frequency. So that assumption allows us to then not consider identity. No, they're all at the same temperature. But what we're going to talk about today with the kinetic molecular theory is that some of them move faster than others, which would then impact the number of collisions. But we assume so many things so we can stay ignorant, so life is easy. Okay. But it said for that last part, assume these same conditions, and it was speaking to these conditions here. That's the only reason we collected them together. Because, and the reason that occurs because after the reaction occurs, well, we've got all these gases in the same container at the same conditions, so that should make sense why we had to make that assumption. Okay, let's look at problem set 1 through 11. I'm not going to go over every single question, but I know you need to check your answers. My bad for not putting the answer key on the bottom of that. I will do textbooks at the end, simply because it is those are in the back of the book if you want to check your answer yourself. So forgive me, it's a little scratchy, but I think you guys can see. So 1A point, I think we actually talked a little bit about this yesterday in class, but as you go, just kind of check with me. 0.123 moles of gas for A. That led you to molar mass of about 28 grams per mole, and most of you guys assume that was nitrogen. If I go too fast, let me know, okay? Dang it. Okay, ignore the red line here. We don't need that. It's going to stay. Okay, so when you plug into your ideal gas law, your pressure should be 2.07 atmospheres. Converting your moles to grams using diatomic chlorine mass is 17.7 grams of chlorine. And then finalizing by getting density, which is grams per liter for gases, about 6 grams per liter, so 5.9 grams per liter. You could have also rearranged the density equation, but if you just have the data to find density yourself. Thumbs up? Okay, so that's not going to work. We're going to do this. 3, so remember, story can either come first or second. In this case, it's coming first. So we took our grams of carbon dioxide to moles. We got 0.82 moles. Plug that into the ideal gas law, and then take our temperature we get, which is in Kelvin, about 337.9 Kelvin. Subtract 273 to get 64.9 degrees Celsius. Thumbs up? Questions? You guys speak now, guys. Okay, I'll do a break in a second. So 4, you had data for the dirt over P equation, so plug that into the dirt over P equation. Noticing that this 2.51 grams per liter, you could technically plug 1 liter as a V for volume into the ideal gas law if you wanted to do that instead. But since we actually have everything for this particular equation, I would use this equation, and that's going to leave us the pressure to be 0.960 atmospheres. Give me a thumbs up and you good. Okay. 5 was just find the density itself. So in terms of, what was given to you here? Did it say just STP? Yeah, okay. So at STP, you know that the definition of STP is 1 mole of gas is equal to 22.4 liters. So that's how you're going to incorporate molar mass and volume together. So in the way that this was described, you had diatomic oxygen. So that's 32 grams per mole. And when you divide that by the molar volume being 22 liters per mole, the moles cancel out, right? So then you have grams per liter, which is density. So that was probably a weird one that you maybe didn't figure out how to approach it, but does that make sense now? Okay. 6, you had yet another, like these equations should be like ingrained in your brain now, right? So you had another molar mass relating to density setup. So then as you solve for molar mass, which is just dRT over P, you got about 44.3. I can't remember if this was 6.0. How many sig figs were here? I don't have my paper in front of me. Just 1. So then we would have to round it to 40. But in terms of sig figs, you guys can modify from there. Number 7, we had to do our stoichiometry from, this was at STP conditions. So from, what's C2H6? Ethane gas, right? So ethane plus oxygen, so we have combustion. So we're taking our grams to moles of ethane to moles of oxygen, and then, yep, we're still dealing with the gas fluid, 22.4 liters per mole, and that says 705.6 liters, which we need to look at sig, but actually that's right, it's for sig figs. Okay? Thumbs up and I can move from there. 8, some folks asked me about, and 11, so that's kind of where I'm going to be focusing. This was electrolysis, which is just breaking down of a compound by throwing electricity through it so it decomposes. So this is water breaking down to its 2 gases. That's for volume total. So I could just, you could set up a BDA where you could just do stoich twice. So since water is our only reactant, that's limiting reagent. So we're going to use that to process forward. So taking your grams of water to moles of water, you can go to mole ratio to find your moles of hydrogen, which is a 2-to-2 ratio. And then same thing, grams of water to moles of water, use a 1-to-2 ratio for mole ratio for oxygen and water. So this gives you 2 sets of moles. And remember, if you're trying to find total volume, it does not depend upon the identity of the gas. So you can continue to take this to ideal gas law as a total mole. So taking moles total between what you just got, plugging to ideal gas law, you should get a total volume of about 224 liters. So you're just documenting a couple of thoughts, right? Problem-solving process. Okay. All right. So this one, there's a ratio wrong there. It was a 2. What are my answer keys now? There it is. So this one right here, I neglected to put 2 there. So the answer down here is twice as much as it should be, but I'll tell you guys when I get there. So number 9, sorry. You were looking for moles of hydrogen gas, and then you were to backtrack to the grams of calcium hydride that reacted to make that gas. So if you start off with your initial information, it's all about the gas. So you're able to find moles of hydrogen gas by just doing PVX and RT, and that's going to give you 0.1817 moles of hydrogen gas. So as we take this now, we're just going to do stoichiometry with this, and this mole ratio between hydrogen gas and calcium hydride is wrong right here. It's a 1-to-2. You guys see that? That's supposed to be a 2. So, and that would then impact our final answer to be divided by 2, so that'd be 3.8, 82, thanks. So that's going to be our stoichiometry process from moles to moles of calcium hydride to grams of calcium hydride to get to grams of calcium hydride. Okay, last 2. So what was her, or, no, 10, they gave you the reaction. You may not remember, but this is like the ion that we formed in alum. So similar situation, STP, you can use 22.4 liters. This was a little overkill. We've done this like 3 times. But once you have your aluminum is forcing the formation of hydrogen gas. So you had to get from aluminum grams to moles of aluminum to moles of hydrogen gas using a 3:2 ratio, and then to liters. So 7.87 liters will work. All right, last one. So this is the one a bunch of people asked me about. So you had your silver oxide, you had some grams given to you that. They told you the decomposition of silver oxide, and this is just a binary decomposition. So you've got silver metal and oxygen gas being made. So now that you know you have a gas, this is the gas of interest. So they told you the gas liters, temperature, atmospheres, and then the water vapor pressure. Water vapor pressure is the water that's embedded in the gas that we need to remove to get just the pressure of that gas. So you're doing whose law first up here? Dalton's law, to just solve for the partial pressure of oxygen. Notice this was in atmospheres and this was in moles of mercury, so you have to come to a common unit before you can do that. So that's 0.9648 atmospheres. Once you solve for the pressure, you can then use the ideal gas law with the rest of the information to solve for the moles of oxygen gas. So plug and chug there. Your moles of oxygen gas is teeny tiny, but 5.4 times 10 to the negative 4th moles of oxygen gas. So this was like our purity. This is like a question that you potentially saw on a test that Chase had taken. So you've got the purity of an ore or of a compound initial. So you take your moles of oxygen gas and you're going back to the original form, which is where oxygen came from. So that's a 2:1 ratio from our BCE, and then you get the grams of the silver oxide. So who got this far? Like 4 or 5 people? Okay. So do you understand now that it's just partial pressure? Plug, he was on our team. We really can't goof this up too much because it's like the same thing over and over. So once you get to your grams of silver oxide, it asks for purity. So it told you how much initial sample you had. Obviously it was not very pure because only a portion of it actually reacted. So you take your portion over your total times 100, 41.8%. All right, stand up for me. You're getting sleepy on me. Stand up and go tell us to me about what you're doing for mole day, and then we'll start our actual notes. Maybe brainstorm on some lyrics. You can throw it down real fast. What you gotta do. I'm going to be working with another student and we'll put some of these topics. If you want to say
Even if you have like the so you're trying to figure out this I just feel like
but once I was yeah, and I'll put it on the website. I gotta get it, but I want to do it.
I encourage you to
most people just the overall all right, Anne, come back to me. Come back to me. Does anyone want a grape before I move on? I don't know, but I got like 3 bags of grapes yesterday and I haven't taken them on. Do you want a grape?
I have a question.
Yeah, okay. Here. What's your question?
If whenever we do the gas law, will the sequence always be at most 3?
No, so good point. Our constants, so any constants are not considered measurements. Significant figures are based on the accuracy or the precision of our measurements. So pressure, temperature, and volume would be the ones that control our sig figs and ideal gas laws. Our constants are not considered measurements, so therefore they don't play into our sig figs. Good point. Okay, so you guys have some notes on this, and you have done a simulation, which had you identify some relationships that up front we didn't talk about, but now we are. You also have a good background of like my talk 2 days ago, yesterday, about the difference between ideal gases and then like the real gases. So, ladies and gentlemen, do ideal gases actually exist?
No.
Okay, so what do we do? What do we do with that? We don't care, right? We're gonna assume. And if we assume, our lives are easier. So that's kind of what we're gonna go with that today, okay? So in terms of like major writing, please don't write down everything on the slide. Some of the stuff's in your packet that I have provided you. So make sure that packet is out. Also, some of it's just basic stuff from your reading guide. So you already have some background there. So when you need a break again, let me know. I could talk for days. You know I can. Okay. So in general, the kinetic molecular theory is a theory, and we always have to propose theories to try to explain behavior that we observe or scientific phenomena that we observe. So as we find things that fit our theory, we're like, yeah. And we keep pumping up that theory. It's like, this is a valid theory. But there are limitations to all theories because not everything fits in that nice little box that we call the kinetic molecular theory. So we do try to make some assumptions to make our lives easier, but in general, the kinetic molecular theory allows us to predict behavior for ideal gases, but we assume most gases act ideally, though we know that when we're not in an ideal situation or in an ideal gas situation, that there are limitations to this theory. So there are going to be some exceptions to this theory, to the theory. Goodness gracious. Otherwise, we are really on the microscopic or nanoscopic level. So the things that we assume are between 2 teeny tiny particles, and that sometimes does not continue to the large scale. So macroscopic and microscopic things can act very, very differently. And that's something that's a little bit above our pay grade. But in terms of what we're looking at from the macro scale, we should be able to explain on the micro scale. Okay? So the theory is just a theory, then we're going to learn about why it's important in terms of ideal gas law. Okay, this is on your sheet, yes? Most of it? Yes, okay, so you have a sheet in front of you with the stuff on it. This is like why I'm going a little faster through this. So we know the 4 major postulates of the kinetic molecular theory. A couple of you guys named these off day 1, and you said, okay, volumeless particles. We assume that they're volumeless, so that the volume of the container is what we say it is. So if I said I had a 5-liter container, well, truly it's not 5 liters of space because the gas particles themselves are taking up some space. But then we got to work with like subtracting the volume of the particles, and nobody's got time for that. So we just assume that they're volumeless so that the particles have the entire space to roam in order to cause pressure differences. We also assume that their collisions are what's causing the pressure, and so as collisions are occurring, they're occurring at different speeds and different, well, I'll say different velocities. You guys know the difference between velocity and speed? Taz, what is it? Okay, so this is a velocity, and this is a velocity because I'm showing the speed by the size of my vector, and the direction is the other part of that. Oh, yeah, just hand, thanks. You can just take a hot second there. I didn't clock in today, so I just got in trouble. Okay, come back to me. Okay, so speed has just a number like I'm moving at something miles per hour. It's just the number, it's not the direction. So what happens is we have to just say speed and velocity are kind of the same for chemistry. That's more of a physics term that we differentiate between. But for example, in physics, if one particle is moving one direction and the other moves the other direction at the same speed, they cancel each other out, so their speed or their average speed is 0, which isn't true for chemistry. We're talking about things colliding with container walls. But that's one thought that we'll talk about later. Okay, so another thing we assume is that they don't have any IMFs, intermolecular forces, because as soon as things start to attract, what do they do with the container wall? If 2 particles attract, so attraction person next to you, just kind of, okay, so you're together now, so what happens is the number of collisions in the container wall? They reduce significantly, right? Because two independent particles can collide. The two particles that are bonded or attracted together collide less. Well, then we got to deal with pressure differences. And we don't have time for that, okay? So we make these assumptions. Another equation that should be familiar with is the average kinetic energy equation. And so R is not the pressure R, okay? I'm sorry, there are like 4 R's in chemistry. We have the rest of the letters to work with, and we chose R. Okay, so this this R in the average kinetic energy equation uses the one with energy in it. What's the energy in it? Joules, right? So make sure that if you're talking about pressure, ideal gas law pressure, you use the one with pressure in it, which is like atmospheres. If you're talking about energy, like kinetic energy, from as it relates to temperature in Kelvin, you're using the one with joules in it. Notice that Kelvin is here and moles are here because it is talking about like the average kinetic energy of a certain number of particles, which is why we have quantities. Those R constants are given to you on your reference table. So all the laws that we've already learned can be explained or supported by the kinetic molecular theory. So I only have really one I want you to like highlight here, but the one I want you to highlight is in yellow. It's highlighted. So basically the things that we have been stating, the relationships we've been portraying verbally, are all supported by the kinetic molecular theory. So this is Boyle's law first, if you decrease the volume, the container gets smaller. What happens to the number of collisions? You increase collisions, therefore increasing the pressure. So we know that, but we are making those assumptions. We actually inherently have been making all the assumptions that kinetic molecular theory makes because that's how we've learned it. So we can explain increase in the inverse relationship between P and V by this decrease in volume, increasing pressure because of number of collisions, which relates back to the second one there. Number 2 specifically, I just wanted to emphasize one point. When you increase the temperature of something, they move faster, right? Right? Okay, so as you move faster, you not only just hit the container more frequently, because you're moving faster, but you hit it with more force. So there are 2 parts that can in fact increase the pressure. So the intensity and the frequency of that collision. And the rest of them kind of makes sense too. Increasing the kinetic energy or the increase in the temperature, which is going to increase the average kinetic energy because of this relationship right here, is then going to cause the container or the collisions to occur more frequently and then increase the pressure. So since you don't want the pressure to increase for this law here, which is Charles' law, then you actually have to increase the volume. And then increasing the number of molecules in all will cause what to happen to pressure? Increase. And so if you don't want the pressure to increase, what do you have to do to the volume? Increase it to make more space so less collisions occur. So the relationships that we've been speaking are all just the laws that we're more familiar with, but all the assumptions behind the scenes are just the kinetic molecular theory. Right. In all, you got the general gist of this? Okay. I'm going to now go to application of this with Maxwell-Boltzmann curve and then Graham's law. We already did this. We talked about this, but the only thing I really want to emphasize, please don't write all this down. Okay, this is the main point. We knew that in the past, 2 days ago, we talked about how ideal gas behavior, the conditions that allow gases to approach ideal gas behavior, what conditions were those? So say what pressure? Low pressure, so they're really spread out, so they don't interact, and what? High temperatures, because they're speeding past each other. Do they have time to interact when they're speeding past each other? No. So those 2 conditions allow for us to assume ideal gas behavior is most ideal. So this is an easy multiple choice question. Which conditions allow gases to approach ideal gas behavior? Like that is, you should know that off the cuff. And then everything else, if you're not at those conditions, so if you're at high pressure and low temperature, things start to deviate from ideal gas behavior. So the deviations just mean that they're starting to act more real. which totally nullifies all of our assumptions. But this is where I would say, what conditions do gases act most real or deviate from ideal gas behavior? High pressure and low temperature, and then some of the following 2, 3, and 4 here are those deviations. So we said ideal gases don't have volume, so the volume is negligible, but real gases start to condense together, therefore we have some volume we're working with. Real gases have attractions, so that those intermolecular forces come into play, and then we've got to deal with how they didn't deviate from the pressure we would have expected. So take a minute and read what's here, and then I'm going to move on to the next page here. Give me a thumbs up when you're good. This is a lecture heavy, less math day. I'm sorry. I'm doing this because Mold Day is Monday. Okay. Okay. So in terms of what we have to adjust for, and this is just in theory we would adjust for it, but we should understand where the adjustments come into play. We adjust because real gases technically have volume and real gases technically have interactions, which would vary the volume and the pressure that we would expect from an ideal gas. So, we have an ideal gas law. There's also a real gas law. And we will not calculate from it, but we must expect that we can understand the pieces of it. So, board just reset, just hold on. Okay, so this is the real gas law. It's a combination of pressure and volume. These are the two pieces that I actually have on the next slide. Let's show that first. Nope. Yep. Okay, so this is the real gas law. Something crazy, right? But we're going to understand the pieces of it, and that's all I want you to know are the pieces and the influence that the realness of a gas can cause. So here we go. The B factor that we see in the real gas law is in relation, or has a relationship with the size of the gas molecule. So what I have here in blue and red are kind of what I would be writing down. So you could say these are like variables in the real gas law. So the first variable deals with the volume aspect that we spoke of. So B, which is the variable that we're speaking to first, is just a correction factor that says, hey, real gases have volume. I've got to adjust the volume. I technically subtract the volume that the particles take up to say, okay, this is actually how much play space they have. This is how much volume they have in the container. We're not actually going to calculate this, period. You just have to understand what the variables are referring to. So since some particles are bigger, the volume will vary based on the size of the particle. So that's why I always say B means bigness. Bigness is not a word, but B means bigness. So if B is referring to the size of the particle, bigger particles take up more space, they influence the volume more. I know you're writing, but you're listening, right? Because I'm simplifying, I'm whittling this down to like just the boiled pieces that we need. Okay, so the other factor is, so this was the volume aspect and this was the attraction aspect. So the A factor, A variable, is going to be impacting not the volume necessarily, but the pressure. So what we have to do is we understand that two particles independently can bounce and hit the container wall and cause pressure. But as soon as those two particles come together, they are going to then have the collisions, which does some damage to the pressure that we would expect they would occur. So we have to adjust for that. So if the particle is polar, well, I'll go with this first. A is going to be just like the little acronym. So B means bigness, A means attraction. So as particles have more attraction for each other, they're going to alter the pressure more. But there's a rule to how things attract. So in terms of attraction, we have particles that are polar and particles that are non-polar. Do you remember a wee bit of this from Honors Chem? In general, which particles have stronger attractions? Well, so like particles have stronger attractions themselves, but who has the strongest force? Well, ionic bonds, but we're dealing with gases, right? So they won't be hydrogen bonding, right? So there's this IMF called hydrogen bonding, which is only present in polar molecules. So the attraction comes into two parts here. Stronger attraction, I'll scroll back up here as I can. The stronger attractions are within polar molecules, or between polar molecules. Stronger attractions are between polar molecules, and then weaker attractions are between non-polar molecules. So we're not going to like learn or relearn polarity and non-polarity right now because that's like our spring topic. But I just want to give you a thought that you understand just how things look, how you can look at a molecule and understand it's polar. So I won't ask too much of this because this is not in this particular unit. But our polar molecules are things like water, ammonia, water vapor, ammonia, and some others. And then non-polar compounds would be things like neon, helium, carbon dioxide, methane. That's a good list so far. Anything diatomic, fluorine, or anything diatomic, they cancel each other off. Okay, so basically what this means is polar molecules have an area in their molecule where you have a partial negative and a partial positive. So like poles of the earth, there's opposite ends. So if you have a polar molecule, you have a negative end and a positive end. That means that you act with another molecule in like a magnetic fashion. So you attract. And weaker attractions, so things that are non-polar, don't have that partial negative, partial positive, so they don't attract very well. So that's just gleaning over that for a moment, okay? So if you have to tell me what the B factor represents, what does it represent? Bigness, which actually means what? Size of the molecule, okay? You cannot say bigness on the AP exam. Sometimes we say things, but it's just to make sure we understand what it is, then you have to say the real scientific term. So then A refers to attraction, which is going to be based on the molecule's polarity. And I also put polarity and size. Do you guys see this right here? Yeah. And that's only because as you break down to the two categories between polar and nonpolar, the larger molecules over here, larger nonpolar molecules have stronger attractions. So if you had two nonpolar molecules, you're like, okay, who's going to deviate from ideal gas behavior more? It would be the larger of the two. So like methane versus neon, something like that. Because methane is way bigger than neon in terms of size and electrons. Right. So can you explain what we just said to the person next to you? Go. Take a minute and try to rephrase what we just said. Yes.
So why would non-polar molecules have a stronger attraction if like polar
No, it's not stronger than polar. It's in their own category.
Okay.
Sorry, it's in their own category. Okay. That's why I try to keep the divide there. Yeah. All right, major questions right now, and then we're going to move on. Yes. Excuse me? So all this side is polar. Is nonpolar. So larger nonpolar molecules have a stronger attraction than smaller nonpolars. Qualify that as stronger nonpolar. Okay. Larger nonpolar molecules have a stronger attraction than smaller nonpolars. Something called polarizability is when the electrons shift around. We'll get there. Okay. Huh? It's not about that. That's about ionization energy and electronegativity. Okay, so this is the Van der Waals equation, which we call the real gas law with those deviations in place. do not, I wouldn't even write it down. Nobody cares what it is, because I'm almost sure it's on your reference table. Does anybody have that available? I just want you to know what the two factors are, okay? So the A, which is the attraction component, is the part that's going to influence how things are going to bounce off the container wall. So the A is going to correct the pressure from ideal to real, and the B factor here, which is bigness, is going to in fact correct the volume that's truly available for ideal real gases. So A, attraction, B, bigness. So in terms of what we actually need to talk about, actually, yeah, I'll do this now. There are charts like this in your book, and so I want you first to tell me, looking at the A values and the B values, okay, so you can see them all here, from the A values and B values, which are the van der Waals constants, blah, 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 blah. So for hydrogen gas, carbon dioxide, nitrogen gas, and methane, predict which of these gas molecules show the strongest intermolecular forces. So what was the other, methane? Okay. So which of those, hydrogen, nitrogen, methane, or carbon dioxide, show the strongest intermolecular forces? Which column are you guys looking at? So intermolecular forces are forces of attraction. So you're thinking attraction, which means which variable? A. Okay, so this one's the one that deals with attractions, which would be intermolecular forces. Okay, so you guys said the biggest one was which one? Carbon dioxide, because it's at a 3.5 versus the rest of them are smaller. So I'm going to tell you guys this now, but this one's nonpolar, this one's nonpolar, this one's nonpolar, and this one's nonpolar. So the reason, okay, so now we know they're all nonpolar, so they all kind of have the similar weak attractions we've been speaking of. How did I figure out potentially that carbon dioxide had the biggest? Not by just looking at it. Say again? So I heard two people say size. Do you guys agree? Remember, attraction is just based on the polarity, but since they're all the same polarity, we kind of just go to the next factor, which was its size, which this one right here, when you draw it out, it has the most electrons in its Lewis dot structure, which looks like marker. Looks like this, C double bond O, C double bond O, and these are octet around it. So because it has the most electrons, then it also has the strongest ability to attract other particles. Questions? So because the question that this was referring to specifically mentioned intermolecular forces, so I have to look at the attraction component. And so I'm staying in this column, but what I mentioned earlier was that you guys had the A value, which is a function of polarity first, and if they're the same polarity, then you're going to refer to its size, but still in that same column. Okay. So going back here, oops, what do you guys notice has even bigger attractions? Ammonia, right? Do you know why? It's polar. It looks like this. H, H. Do you guys remember drawing those dot structures? Yeah, that's polar because there's this big partial negative up here, and there's a strong partial negative or partial positive down there. So it's polar, so it actually has the interactions of hydrogen bonding. So it's going to be even stronger in attraction, so it would deviate the pressure even more because it won't attract, or will attract other particles. Okay, and then that's kind of what we'd be looking at. And then I just want to show you this chart. So just take a minute and look at this graph for a hot second. The first one and the second one, they're kind of small, but I'll show you where these are. Okay, so this first graph, is just representing, you guys can see P is on the bottom, so the pressure is increasing across the x-axis. So ideal gases, we expect that this, whatever this is the ideal gas law stays constant. But as you increase pressure, look at all these real gases. You're at low pressures, you're kind of close to the red line. But as you increase pressure, what do you start to see? deviations, right? So it's deviating from ideal gas behavior at high pressures. And then over here, this is looking at, I don't know if you guys can tell, but these are Kelvin, Kelvin, Kelvin. So at, they have the temperatures here, but at low pressures and these temperatures being what they are, you see it's close to ideal behavior. But as you increase the pressure and increase the temperature, the ones at the, this is 203, 293, 673, which one deviated the most? 203, so that was low temperatures. And why are things deviating at low temperatures? They're slowing down, so they're more likely to attract, and so then they start to deviate from ideal gas behavior. All right, so this isn't like a super hard concept, but I just keep repeating it because this is where all your multiple choice questions fall, is just knowing it well so you can be fast with it. All right, so the last part, I'm just going to show you the kinetic energy equations. We'll do some calculations and we'll wrap up. Do you guys know your two kinetic energy equations? K equals, so KE equals 3 over 2 RT. So 3 RT over 2. What's the R value? 8.314 joules. Right, so joules over mole K, or just the one with joules in it, we should know. If you have your reference, you guys have your reference tables out? Do you see that R constant? Pull it out so you should look at this because you get this on your test all the time. Okay, so the other one deals with mass and velocity. Does anybody know that one? Maybe from physics? Kinetic energy. You got it. Come on. Kinetic energy equals 1/2 mv squared. Good. Okay. So the first one we already know about. This is the one that we just mentioned, and I will just put this back up here for you. So we know this relationship between as temperature increases, then kinetic energy increases, and that's by nature of the kinetic molecular theory, where temperature or kinetic energy, average kinetic energy, is dependent upon the temperature in Kelvin. And we are going to use this on the Maxwell-Boltzmann curve, which is this curve that looks like this. You guys remember drawing those and superimposing them, right? Cassie, did you ever get the superimposed graphs on the Google Doc? So we just drew it. Okay. So the other equation is one that you have maybe mentioned, but you didn't actually write the equation out. You guys have in your simulation fat molecules and skinny molecules, right? The heavy ones moved slower, okay? So there is an inverse relationship between mass and velocity. But I'm saying this too specifically because we're assuming these are at some constant temperature. So if I'm at a constant temperature, which of these variables has to remain constant? Somewhat constant. I'm trying to relate kinetic energy back to temperature. So if we have a particle with a specific kinetic energy, then as the mass goes up, the velocity of that thing goes down because this is related to the temperature of the system. So if I have some kinetic energy, a light particle, meaning the mass goes down, with this being a constant, the velocity has to go up. So that kind of makes sense. If I were on the cross-country team, I would be the slow one, so I'd be this bottom one down here. So you'd have some people moving fast, some people moving slow, just like in the gas particles. You guys saw them moving everywhere, but as soon as they hit the wall, they might even slow down, and we assume that they have elastic collisions, but truly they have inelastic collisions because they do lose some of their velocity. So we are going to reference the Maxwell-Boltzmann curve here in a second. Okay, this looks like a mess. This is on your paper though, right? Yes? Right. There's some background theory, but I'm going to kind of just get to the parts that are necessary, which is the math side of things. But between temperature, kinetic energy, and velocity, we have to be able to relate these together in a lot of ways. But the real math comes in just as, can you calculate the kinetic energy of a particle? And can you determine its rate of effusion or diffusion? So the background to this is relating temperature to kinetic energy to velocity, which is related back to the kinetic molecular theory. We call it U, which is actually a V. It's like a mu. You know what mu is? Mu is like this. They kind of draw it like that. But I usually do U, or you could do V like that. They're all the same thing. But we're representing velocity of a particle, a gas particle. Realize that in chemistry, we're calling speed and velocity kind of the same thing, okay? So temperature is not a measure of the speed of a particle at all. Remember, temperature is equivalent or relates to the average kinetic energy of all the particles, because, like we said earlier, some particles move fast, some particles move slow, and they're moving in different directions. So we do have to consider the temperature to be related to the average, because as things collide, they start to slow down occasionally. So what we're doing is we're relating this kinetic energy equation to this kinetic energy equation, which includes the velocity of an average set of particles versus the velocity of one particle. And this is all particles. So we don't always calculate for one particle. A lot of times we calculate for all particles. So this is called root mean square velocity, which RMS, root mean square velocity, and that is our velocity of the total sample of gas particles at a specific temperature. So, as you might see up here, the kinetic energy, which was equal to 3RT over 2, that's what I've incorporated here, except I dropped the 2, and I'll maybe reference that later why. There is a way to derive this equation. We probably won't have time for that. But this is the equation you should know. Not on your reference table. It's not there. Pretty sure. So let me tell you what that says. This says U RMS, so we just call it ERMS, root mean square velocity, is equal to the square root of 3RT over molar mass in kilograms. That's why I say kg. Molar mass in kilograms. And that's simply because we're dealing with force. And those of you who took physics, force deals with newtons. Newtons deals with kilograms. So there's background content to this, but it's just you're dealing with kilograms. Remember, again, we are dealing with energy because it's speed, so we must be mentioning the R constant with the joule in it. But as you know, joules is a form of energy. It's actually the energy that's like force per area. No, newtons are force per area. Physics, okay? But joules is equal to kilograms times meters squared, or meters squared over second squared. What we're going to do by nature of the square root here is we're actually going to whittle this down from meters squared to over second squared to just meters per second. And meters per second is a unit for velocity. Like when you travel to school, you travel at miles per hour. We're talking about really microscopic things, so they're traveling in meters per second. They're traveling very fast. So that's how the square root and this little unit comes together. So this is the theory behind it. This is how we're going to do a calculation, but we also should be able to read a diagram with it, which is the Maxwell-Boltzmann curve. And so the Maxwell-Boltzmann curve, which kind of looks like this, is a bell curve. And it's supposed to represent all of the particles at every speed they travel. So you've got some traveling quite slow, you have some traveling quite fast, but we really are concerned about this average here. And so that's why we have to show the full distribution so that we can see the average, and we'll then compare different gases, and then we'll compare them at different temperatures. And that's on the next slide. And this is what you guys introduced within your simulation on Monday, Tuesday. Is some of this background coming back to you from the experiences you had? This up here is new, but we'll form it into Graham's law, which is not new, so you'll see the constants here. All right, give me a thumbs up if I can move on. Okay. Tell me, let me see your paper. I can't remember what paper it is. Good. Okay. So this is the curve, but you notice that I've labeled these 4 curves with different what? Temperatures, Kelvin, Kelvin, Kelvin. And I'm specifically talking about oxygen gas here, so the constant is the gas itself, but I'm looking at all of them on different temperatures. What do you notice about the high temperature ones? They have a wider range. Okay, so there are 2 things you should be realizing. The 2000 Kelvin here has a wide range of velocities because the hotter you are, the faster you go. But not all of them move faster. A portion of them move faster. So we notice that they have, at high temperatures, they have a bigger range. And what can you tell me about their average speed? Also higher. So the average is kind of right at the peak, right? So they have not only a wider range, but they also have a higher average velocity. Okay? So what do you notice? Give me the same story, but for the 273 Kelvin. Okay, so smaller range. Look how little this one is. Way down here. Okay, so here's the range. So it has a lower range and a lower average. Okay, so if you can see the numbers down here with the speed as meters per second, can you tell me the average speed for the at 2000 Kelvin? Approximate, please. So again? So 1300-ish, okay? So average speed is 1300 meters per second. Like insane. Like I don't even know, that's what, is that 13 football fields? Okay, yards, but meters, okay. That's huge. So otherwise, at colder temperatures, at low temperatures, we have lower average velocity and a lower range. And what is the velocity there? Average velocity? Like 500-ish, maybe a little lower even. So I'm going to say approximately 500 meters per second. Okay. Say again? Oh, that is 250. That says 250. There we go. There we go. So where have you maybe have experienced this in real life? Particles moving fast and slow at different temperatures. Okay, state changes. All right. So we're talking about gases, right? How do we detect gases? Okay, we wash them. So we would only be able to technically detect them with the sense, not with hands, not with sight, not with hearing. Oh, here comes the gas, guys, right? So you're not going to do that. You're going to smell it. Okay, so maybe if something's warm and it has a great smell, like homemade cookies, that just smells wonderful, right? And the gas particles are smacking you in the face. You're like, now you're targeting your brain's like making you grumble, or your stomach grumble. So how does cookies smell when they are like just cold? It doesn't really smell, right? So the particles are not really hitting your nose because they're not moving as fast because they're not coming off the source as fast. So that's just a good example. I was going to use like leftovers in the fridge, but not a good example. Yeah. So that's what I'm going to get to next. So this is like kind of a calculus concept, I think. But what you should notice is under the curve, the area under the curve. Is this right, calculus? Area under curve is the same between the green curve and the blue curve. Okay? It's not a lie. Well, it does not look the same, but we have not changed the number of particles, so the number of particles stay constant across this entire situation. So one thing you should note is, I think I have this down here. Temperature changes the shape, and this is me screaming at you. Temperature changes the shape of the curve, not the area under the curve. You will get multiple choice questions wrong if you do not know this. Because this is a quick look at the curve, okay, well, this one's the same approximate area. You're not totally diminishing and like destroying matter. Yeah.
If you have a different number of molecules, would you have a different comparative curves like that?
Yes, and that they wouldn't do that to you because they want to change one variable at a time. Right. All right, give me a thumbs up when you're good with Maxwell-Boltzmann. Okay, so I'm going to try to squeeze 1 Graham's law in here. And then what I don't finish, I'll finish more like Tuesday. Okay. We don't have time for that. Oh no, but we can do this. So we're not going to do the mathematical proof. I didn't think we'd have time, so we don't. Can you guys look back at the equation you just wrote for velocity, average velocity, root mean square velocity? What was the equation? Square root of 3 RT over M in kilograms. Okay, so let's do this quick. Square root of 3, what's the R value? Joules per mole. K. Okay. And then what's our temperature here? 293. So we took 20 plus 273 divided by, yeah, so in molecular chlorine means diatomic chlorine.
70.90.
So it's 70.90 grams per mole. So it's 0.07090 kilograms per mole. Yes? And then square roots all the way down here. Okay. So what units cancel? Moles and moles, and this is denominator, right? Denominator, this is a numerator, Kelvin and Kelvin. So what are we left with? Joules per kilogram, which doesn't sound like speed, but we're going to convert that in a second. So can you guys calculate that for me? While I find my differences. And can I get a speed? Square root. 321. And this is going to be in what units? We already know the units. Meters per second. And that's because as we square root this, we get the square root of joules per kilogram, right? What did I tell you a joule was? So a joule is technically kilograms times meters squared per second squared. Okay, so if this is what a joule actually is, what cancels? Okay, and what's the square root of meters squared or second squared? Meters per second. Okay, you don't have to convert it. It's just if you write the wrong units, I'm going to count the units wrong because we all know speed is not joules per kilograms. It makes no sense. So please write it as meters per second if you're talking about velocity. Okay, Graham's law. I got this. I got 10 minutes. This is just, oh, by the way, this is the, well, yeah, I'll stick with this. This is just the speed of molecular chlorine at this temperature. And we are considering this to be the average because this is at a specific temperature. Okay. Okay. On this graph, this is not Graham's law yet. On this graph, can you guys tell me T1 or T2, which is higher temperature? T2. It should be a quick answer because you see what? Bigger range and higher average velocity. Okay, and then something you'll notice too is that you see how the curves are shifted so that it whittles down on the right hand side. More of them travel at like 75% of the speed and lower, right? There's not as many that get to the high speeds, and that's because things get in the way, like other gas particles get in the way. Okay. I'm not going to do this, but I'm sorry. I had all kinds of fun planned for today. Graham's law. Okay, this is something you learn in honors chem. Graham's law of diffusion. Who remembers something like this? Maybe the term Graham's law. Okay, so if I brought in a box of Krispy Kreme donuts for mole day, donut moles? Donut moles. Okay, so, okay, I'm going to make a note to myself. Mole donuts. Okay, so if I brought in some of those and they were fresh, you would smell them upon me entering the room because the gas particles are diffusing out to you. But are they smacking in the face at 300 meters per second? No, because what's in the way? All these particles that the air is made up between you and I. So they actually effuse or diffuse. We kind of use those interchangeably sometimes. They effuse or diffuse in a really sporadic pattern as they move around the room. Okay? They don't travel in a straight line right for your nose because they're not looking for you. So it looks like a trial. But they do travel, but it's at a much, much, much slower rate because stuff is in the way. So one thing, that's kind of more the definition of diffusion. You're talking about the gradual mixing of one gas with another, but they're still moving at high speeds. It's just there's stuff in the way, so they move really erratically. And then the definition specifically of effusion is the escaping of a gas particle through a hole. So example of a pinhole in a thing that contains a gas. No examples? Popping a balloon, thank you. Okay, so balloon, gas particles travel out. So that's effusion. It's not a vacuum, but it's from a container that's closed. So these are your two definitions. You have this on your paper. Moving on. Okay. So we apply these definitions and the kinetic molecular theory and the kinetic energy velocity equation via Graham's law. And this right here is generally how we use Graham's law. It's a rate comparison. It's not just like, hey, what's the rate of molecular chlorine? It's what's the rate of molecular chlorine compared to oxygen. It's a comparison. So, if you remember this from last time, give me a thumbs up. You can say no, it's okay. It does not hurt my feelings. Okay, so basically what you'll notice is that in this proof right here, I have 3RT over molar mass 1 over 3RT over molar mass 2 and square root. What happens when you divide a fraction by a fraction? Copied out floppy, and then you move on. It's the 3RTs are the same, so we're canceling those out. So then ending, we have molar mass, what on top? Molar mass, what on top? 2, because remember they flop, over molar mass 1. So that's just how we get the inverted relationship. Okay? It's not just like I messed up, it's inverted relationship. So rate of gas 1 is always going to be the lighter gas, so you get a number that makes sense. Because if you're like, yeah, gas particle A moves out 0.35 times faster, it doesn't really help. You know what that means, slower. So if you always put a lighter gas on the top, then you'll have like rate of gas A moves 3.5 times faster, meaning it makes more sense because you're saying it's faster and it legit is faster. So we're going to do an example with this, okay? Ready? So rate A over rate B is equal to square root of molar mass B over A. Use grams per mole here, no need to use kilograms. All right, let's do this one first. Okay, compare the rate of diffusion of carbon dioxide and oxygen gas at the same temperature. So, rate of who goes on top. So we're looking at what to determine that? Say again? The lighter gas. Who's lighter? Oxygen gas, right? So what's carbon dioxide's mass? 44.01 grams per mole. Molar mass of oxygen? 32 grams per mole. Okay, so we're going to do O2 on top and CO2 on bottom. Okay, so now in my molar mass relationships, whose number is going on top? Carbon dioxide. And on bottom, 32. And, okay, that's like 1 and some change. Greater than 1 and some change is what? Where is this squeeze? 4.17.
1.17.
I was like, it can't be 4. Okay. You guys know I'm deaf, right? 1.47.
1.173.
1.173. Where am I getting 4? Okay, so what does this number mean? On it, loud and proud. This is the rate of infusion of neither of them. So this means that oxygen gas diffuses blah 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 times faster than CO2. This is not the rate of fusion of either. Remember, this is a rate comparison, so it's not defining either one. Yeah.
How did you decide which one on the top was the one?
We put the lighter one on top. Always. And it will always work out so you're not getting some funky 0 point something. All right, can you guys try to do this one on top? And then I'm going to decide on Because it says this one travels, unknown travels faster, meaning it's lighter. So faster things are lighter. All right, so you guys squared both sides, and then you got 32 over x is equal to 1.5876, and then you did what? So put x on both sides, and then divided by what? 1.58, or yeah, that number. And then x became what? 20.156, and that's in grams per mole. This is an identity of a molar mass. And who is this? Neon. What's your questions, JT?
How do you know that function?
So I knew that in terms of setting up my rate over here, that the faster one was the noble gas. So it was lighter. If it's faster, it's lighter. So then as you do your molar masses, it's inverted. Okay. All right, so what I have, and I have some questions to do today, but I'm not going to do this. So do you guys see this up here on the board homework? All of this is due Tuesday. I know you're going to focus on multi t-shirts because they're going to be awesome. And your lyrics, you know, that exams are going to have. So find in the separate papers you picked up, like, you know, yesterday, you guys have those free response questions separate. They just say FRQs, free response questions. If you don't know who they are, let me know. But I want 1, 3, and 5 done on Tuesday. And then these textbook questions should be related to your kinetic monthly theory. And then we'll be good. All right, good job, guys. Thanks for pushing through today. A lot of theory today.